All right, it's our member Melinda Callis. She joined AAI back in 1984.
I was like -7.
Yeah, that is -6.
Yeah, right.
And she's also a member of two other astronomy clubs, NJAA and Stellafane, which is located in Vermont. She did CPA and finance work in his working career. She also taught roller skates. I thought that was very interesting. And there were some competitions too with the roller skates. Right? Yeah. And she's given a lot of presentations here at Sperry before. So with that, Melinda, go ahead, take it away.
All right, so when they asked me to do this, I was thinking, what am I going to do on Black Friday? So I thought, okay, why don't we stick with the theme and do dark objects? So here's some, see the dark lanes in this. This is that is NGC 4565. It's 40 million light years away, and that's about the size of our Milky Way. But it's a beautiful edge-on galaxy. So you can see the dark lanes in it. This is, of course, a black, a Black Friday mob from years ago. So, okay, let me get my, whoops. I gotta find, here we go, okay. All right, so what I'm gonna talk about, do a little introduction. I'm gonna talk a little bit about dark matter and dark energy, talk about black holes, dark objects and dark areas of the sky. I'll end with Olber's paradox, which you may or may not know what that means, but I'll talk about it. And a little summary in my credits. So again, the topic is inspired by the colloquial name for the day after Thanksgiving. Astronomers usually talk about the bright things up in the sky because there's a lot of really cool looking stuff. But there's a whole lot of dark out there, and it's really interesting stuff. So like light, dark isn't equally distributed around the space. So, and we'll be ending with that question pondered by mankind from millennia. So dark matter. This is a very interesting topic. You'll see a lot about this. It's current astrophysics. So it's something you'll hear about in the news sometimes. My phone is smart enough to know I'm interested in astrophysics, so I get this stuff all the time. So if you ask your phone for those kinds of questions, it might actually put you into that mode. So it's a very mysterious, invisible substance. We think it's about 25% of the universe. Does not interact with light. We have to infer its existence because of its gravitational impacts. It bends light from distant galaxies, and it was originally discovered because galaxies were rotating too fast given the actual mass of the galaxy that we can see. There are multiple theories on the nature of of what it is, and it's believed to be very cold and very slow moving. One of the best examples we have that is considered good evidence of its existence is the next slide I'll show you, which is the bullet cluster. And it's the collision of two different clusters, and they use the imaging from 3 different observatories to combine this one image. It's 3.8 billion light years from us, and the blue in the image is believed to be dark matter. The normal matter appears pink. So here's that image. And we think this blue here is actually dark matter. It doesn't appear blue. This is because otherwise we'd be able to see it. It's the computer processing that allows us to see that. But very interestingly, just this week, there was a new released photo. This is based on 5 years worth of observational data. And this is the Milky Way. And this is believed to be the dark matter that surrounds the center of the Milky Way. Interestingly, they think what's happening is that it doesn't interact very much with other matter, but if two particles of dark matter interact or collide, they annihilate one another and create a little bit of radiation, gamma ray radiation. And so this is basically gamma ray radiation that is of the size and quantity that we think we have dark matter in the Milky Way. And that's why they think that's what they're looking at. But there's a whole lot of science that has to go on to validate this and make sure that that's indeed what's going on here. But I just wanted to let you know that the new things are being discovered every day. Similarly, there's dark energy. Like dark matter, it's invisible. The first time, it's first believed to be it was predicted by Einstein, and the term was first coined in 1998 by Michael Turner, and the name stuck. It's a very, very substantial percentage of the universe. Again, it's cutting edge physics, but we really know very, very little about it. So here we can tell you what its properties are, but we have no idea what it is. We know how much there is. We know that what it does, it expands the fabric of space. It allows galaxies to move away from each other faster than the speed of light. We believe it might not be a constant. It might actually be evolving and changing over time, which is different than what Einstein originally thought. But as yet, we have no idea where it came from, what it is, what it looks like. So, but I have a photo of it. Not really. We really don't know. Okay. So, what is the difference between dark energy and dark matter? So, they're not the same thing. They're both mysterious in the subject of current astrophysical study. We at least have some possible candidates for what dark matter might be, deep into particle physics. We really have no idea for dark energy. Dark energy seems to be ubiquitous, so it's throughout the entire universe, and as far as we know, it's scattered kind of evenly throughout. On the contrary, dark matter seems to be concentrated in galaxies and large structures. So that's a big difference. Mapping dark matter helps us understand the universe's accelerating expansion. And if you think about it, we have to have dark energy out there, because without a force acting on the matter, we wouldn't have accelerating. But we do have the universe expanding at an accelerating rate. So this is the content that we really think that the entirety of the universe is about 68% dark energy. So more than half of what's out there, we haven't a clue what it is. So, and then dark matter, which we only have a vague clue of what it is about 25%. So normal matter is 5%. Everything we know from normal matter, that would be all the moons and stars and galaxies and all that other stuff, and what you're standing on and what you're sitting on right now, is 5%. So a nickel out of every dollar, that's how much we actually can see. So this is why I think dark stuff is kind of cool. All right. So a little less cutting edge, but still cutting edge, in black holes. We had observational evidence of its existence. We could see their gravitational impacts. We could see the X-ray emissions from them, where not all of them, but you see it from wherever it's stealing gases and other matter from a nearby star. The first image was from 2019 using what's called the Event Horizon Telescope, which is actually 3 different telescopes operating in conjunction. And it saw the supermassive black hole, can't talk tonight, at the center of the galaxy known as M87. And here's the picture of it. That's the actual image of the black hole, and this is what it looks like in regular light. Yeah, really cool.
That's cool.
Of course, as I'm sure all of you know, there's all kinds of wild science fiction wrapped around black holes and what they might actually do. Much of it is not so likely to be true. Okay, continuing on then a little bit, it does capture everyone's imagination, and that's why we have the cool science fiction stuff about it. But they are real, and we have learned a lot about them. They consist of objects that are too massive to allow light to escape. Was first conjectured actually in the 18th century because we had started to understand that early on how big stars really were. It was Albert Einstein in 1916 in the theory of general relativity, though, that actually predicted them and what they were actually consisting of and did the math behind it, at least some of the math behind it. And and its general relativity is not the E equals mc squared. This is the kind of relativity that I would have to get another 50 points in IQ to be able to do. So, but and Schwarzschild at about the same time found the first modern solution of general relativity that could characterize a black hole mathematically. So you'll see his name when we talk about black holes a lot of times. The Schwarzschild limit was where anything beyond that is closer to the black hole than the Schwarzschild limit is going to go into the hole, whether it's light or anything else. So it took about 50 years between the theory and observation. The first one observed was Cygnus X1, 1971. They are typically formed when a very massive star reaches the end of its life cycle and collapses inward. And they're often found at the center of galaxies. In fact, some of the ones at the center of galaxies are super, super massive. The idea of it's the ideal, it should be ideal there, black body. It doesn't emit, reflect any light. So then, how does it detect? So, as I had mentioned before, the main reason we can detect them is, well, saw the photo, they're starting to get visual, but they have to do that detection in something other than visual light. Okay, that's the high-tech stuff. What's the fun stuff that we can see? Well, there's the dark spots on Neptune, there's dark comets, dark nebulae, a whole bunch of them there, and then there's the Boötes void. So dark spots on Neptune. There are large hurricane-like storms in the planet's atmosphere. They're similar to Jupiter's red spot, but they aren't as long-lived at all. Jupiter's red spot has been there since Galileo first observed it. These disappear, and then some have reappeared. The first time that we saw them was in 1989 from Voyager 2, and that spot lasted about 5 years. Others have since been observed. They are believed to be like the red spot in that they're anticyclonic, which means they rotate in the opposite direction than expected. We don't know why they're dark. It might be that we're actually seeing down into the lower clouds, kind of like a hurricane when there's a big cloud, but at the center of the eye of the storm, you can actually see down into the ocean. Possibly. There might be a chemical composition difference in that area as well. But you would never want to be there because the incredibly high winds, up to 1,500 miles per hour, which is Mach 2, is double the speed of sound. So I can imagine how that would sound. So there's the dark spot here. You'll notice it's really quite dark in the middle. So that's, I think, why, at least I think, that the most likely answer is that you're seeing down further into the atmosphere of the planet. All right. Continuing on, let me make sure I catch up with myself here. All right, dark comets. This is a new designation, relatively new designation. The first object of this kind that was observed was in 2016. It's called 2000 2003 RM. It was a suspected comet, but it never developed a tail. And its orbit is somewhat different than typical comets, which are very elliptical orbits. So the term dark comet was popularized in 2023. Again, they do resemble both asteroids because they have no tail and they're low albedo, which means they don't reflect much light. But they're comet-like in their motion. Some of them have very unpredictable orbits, and we think that might be because there's outgassing. But it's not the entire object outgassing. It's coming out of one side or one point, and it's making it move out of its original orbit. So there are two kinds that have been observed. There's ones they call the outer solar system that have a highly elliptical orbit. So they tend to be bigger. Bigger in this case still means only like hundreds of meters across. So these are relatively small items. The smaller inner solar system ones have nearly circular orbits and generally orbit the sun. So far, a total of only 14 have been confirmed, the first in 2022, and the last 7 were last year. Their unpredictability makes them of great potential risk to the Earth because we can't tell for sure if it's going to become come close to the Earth and possibly be of danger to us. So they're getting studied a lot as well because of that potential risk. So there's no photo of any of them yet. This is an artist's conception. So it's obviously not. It's small enough that it's not going to be round like a moon or something like that. It's going to be rough. It's dark, which is the low albedo. Albedo being the percentage of light reflected off an object, and it's probably outgassing, which is showing there. That's distorting its trajectory through the sky. Okay. All right, moving on. Dark nebulae. Dark nebulae are interstellar clouds made of molecules and gases and things. And those clouds get in the way of our ability to observe what's behind them. It obscures visible wavelengths. And the dust grains are cold and dense and absorb light. And size matters. There are some really big ones. They call them giant molecular clouds. And then there's these smaller, what they call them, Bach globules. From after the astronomer that studied them, one of the astronomers that studied them. We can see behind them, though, by looking at radio images and other infrared and stuff like that. So we have some idea what's behind them. The dust particles in those clouds tend to be very tiny, and they're often covered with other chemicals, some of which are very, very light absorbent. So that's why they're so effective at blocking light. They're irregularly shaped, and they're often in the sites of stellar formation, which makes them very interesting to us. Sometimes they're associated with naturally occurring masers. I probably shouldn't get into this, but it's microwave emissions, and the first one was discovered and confirmed in 1965. And I suppose I tend to mention that stuff because so much of this stuff has been in my lifetime that we've actually discovered and started to understand this stuff. So, okay, I'm not a kid, I get that, but just gives you an idea of how much astronomy has expanded in a relatively short period of time. And I've got a couple of examples of dark nebulae. This is NGC 2053. It has a lot of dark matter in the outer reaches of it. So you can really see over here a lot of dark. So there's you can't see a lot of the stars in regular light. Really pretty. So this is the Trifid Nebula, and It probably would be very beautiful even if we didn't have the dark matter, but having the dark lanes in front of it makes it almost floral and really a particularly gorgeous item. And one that astronomers, amateurs like to find in their own telescopes. Some more is right here. This is multiple things. Have horse head, have all this black in here, and that is definitely molecular clouds that are between us and the star-making regions behind them. And this next one is interesting because this is a very recently released. It was released. This photo was released about a week ago. It's an unusual galaxy that they can't quite classify it under the usual types of galaxies. It's very, very densely populated. Look how there's like no definition in the middle. And then look at all the darkness around the outside. And look how compact this is. Very, very interesting galaxy. So let's look at a couple of other specific ones that are famous. The Coalsack is a prominent dark nebula, dense cloud of interstellar dust, 600 light years away, so it's relatively close. It's part of Milky Way. Is in the southern constellation Crux, so don't run out and hope to see it because you won't, not in New Jersey. It's a conspicuously dark patch against the bright background of the Milky Way. Easily visible naked eye, so even people before they had telescopes had seen this. So a lot of the indigenous peoples had names for it, and a lot of them you associated it with birds. Not sure why, but they did. Probably because birds are up in the sky. The first Europeans to record it was Yanez Pinzon of Spain in 1499, and originally dubbed it the Black Magellanic Cloud. And the Australian Aborigines called it the head of an emu, but even the South American indigenous people had used bird names for it too. So what does it look like? That's what it looks like. So really nice stellar background. So it really gives you a lot of detail on all the darkness. So someday I would like to see that, but I have to travel. Oops, we'll have to travel to do that. Okay, dark lanes. Well, we've actually seen some of these pictures already where galaxies have darkness within their structures. They were once thought to be holes in the heavens. Nobody really knew for sure what they were. But what we know now is they consist of gases and dust obscuring our view of the stars beyond, at least in visible wavelengths. And again, they're often areas of stellar formation. There's one in the Great Rift in the Milky Way. Stay tuned. We're going to go to that next. Prominent in other galaxies, such as the Sombrero Galaxy and the Black Eye Galaxy, can significantly reduce the overall brightness of that galaxy when you're observing it at a telescope, because you're only looking at visible light. And it's exclusively made of ordinary, that is not dark matter. So it's part of that 5%. So that's the Sombrero Galaxy. You can see the dark rim around the outside, which is what lends to its name. And of course, the Black Eye Galaxy, because it's very, very dark, especially in this area. And when you look at it in an amateur telescope, it will really seriously look like a black eye. This is a professional telescope picture, so it's got a lot more detail. Still, just a beautiful item. Okay, the Great Rift is the Milky Way's example of dark lanes. It's also known as the Dark Rift or the Dark River. It's a band of interstellar gas and dust, obscures the center of our galaxy as viewed from our suburban location in the Milky Way, and it's obscuring mostly invisible light. The core of it is in the western part of Sagittarius, which is relatively low in the sky when you can see it, and it's entirely obscuring the core of the galaxy from our vision. I don't know that anybody's actually, I couldn't find any reference to this, but I also think it might actually protect us from radiation. Okay. We do see modern instrumentation that can look at more than just visual wavelengths, actually can see behind it. There's a lot of star formation going out there. And they estimate there's about 1 million solar masses, in other words, the mass of our sun times 1 million, that's found in the Milky Way. We've known about it for millennia, but at first, but knew about it from visual, naked eye aspect, not just we didn't know what it was. That was again a hole in the sky. It first drew modern attention in about the 18th century because they were starting to say, hey, we can see a little bit of detail here, but it still can't tell us what it is. So it really wasn't explained until the 20th century. So this is a nice professional image of it. Just so you know, this is one I took in a 10-second exposure on a iPhone 12. My new phone would do better than that. And that was up in Vermont where I took it. So it's that obvious. The color in there is a little bit fake, false. The computer did. I clicked on enhance it. It went a little overboard on enhancing, but it's just gorgeous stuff. And I have a little story. One of the observers from NJAA that I knew, and he had been an observer all his life, and when he was, I guess, in his 60s or something, he and a friend of his went out to Death Valley, and he looks at his friend and says, "I'll be darned, here we are in Death Valley, and wouldn't you know there's a cloud up there?" And his friend said, "That's not a cloud." That was that obvious when you're in really, really dark skies. I like this shot because you can see it with the observatory there. Had to include it. So this shows you how much it spans our sky, because this shows all the these, you barely see them, I imagine back there, but these are the names of the various constellations that it crosses. Taurus here, Orion, Cassiopeia, can't see them myself, Corona, Australis. So it really spans a large portion of the sky. Mucus, yes. So it's a very, very prominent thing at night. And if you're in a dark sky area, it can knock your socks off. And you don't even need binoculars that are enough to see a really nice view of it. Okay. Another really cool type of object are Barnard objects. Edward Emerson Barnard and his niece Mary Ross compiled a list of these dark nebulae. And I mention this because everybody talks about Barnard objects. They're called Barnard-Ross objects, but she was as important to this as he was. So being female scientists get mentioned. They've started photographing such objects in the late 19th century. And you can imagine how laborious that must have been, because back then, photography involved massive amounts of equipment and lots of manual processing and long exposures. So, but that's when they started doing it. So Barnard and his niece published in 1919 the original list of Barnard objects, which are dark objects, very obvious dark objects in the sky. And they eventually listed 369 of them. In general, these are objects that lie in the Milky Way and are relatively nearby, most of them are molecular clouds that obscure what's behind them. So we see them not because of seeing them, but seeing what's behind them or around them. With the exception of Barnard's Loop, which is a large emission nebula within the Orion molecular cloud complex. And I promise I'm not going to tour the entire catalog, but I have a couple to show you. These are the ones I'm just going to show you. Barnard 33, also known as the Horsehead, which we actually saw in the one previous thing. Barnard 68, which is one of the famous ones. And Barnard 150, which is also known as the Seahorse. Now, can you guess what animal I like? Yay! And dogs and cats and all that stuff. So there's the Horsehead. Beautiful. Yep. It's a gorgeous photo of it. But there are many members of this club who are very good at taking pictures of this and have things that are almost to this quality. And this is a very professional one. Here's Barnard 68. And you can see how completely it obliterates light in the center. And then there's the seahorse. It does kind of resemble a horse. The seahorse. Here's the head and the long, skinny body.
Sure.
Yep. And it must be a female because it's not pregnant. Okay, the Boötes Void, this is also known as the Great Nothing. It's in the herdsman. Boötes is the herdsman constellation. It's a massive, nearly empty region of space. It encompasses 330 million light years just in diameter. It was first discovered in 1981, again during my lifetime, by Robert Kirshner and his colleagues during a galactic redshift study. So in that area, there are far fewer galaxies than anywhere else. There are approximately 60 in there where there would ordinarily be thousands. We think it was formed that way in the early universe. It's about 700 million light years from Earth. It's not to that, and it's if not the largest, it's one of the largest. So it's considered a super void. Okay, so this is. It doesn't look like a void at first until you realize these are all local stars, and then all these clusters are very distant objects that are around it. So you can see that within that circle, there's really not much going on. There's some local stars, but there's all that dark space behind it. And here's another image. This is actually a three-dimensional representation of the studied universe. And here's the Boötes Void, this big area here where there's basically nothing. There are other voids, but that's the big one. And again, the particle physics and astrophysics kind of collide here as they try to figure out why do we have so much variation in the density in the universe. Okay, said I didn't end with an old question. Olber's paradox was put forth in the 18th, 19th century by a German astronomer, Heinrich Olbers, in 1823. He is by no means the first person to suggest the paradox, but his name became associated with it because he popularized it. And the concept goes that if the universe is infinite, and it was believed to be that, and full of stars in every direction, and stars are eternal, then why isn't the night sky completely bright like day? Kind of makes sense, right? Well, it wasn't resolved until modern science, basically 20th century and maybe a little bit in the 19th. And we disproved the conjecture because the universe is neither finite nor static. Stars and galaxies are not evenly distributed, as we just saw with the Boötes void. Stars are not eternal, and the redshift from the universal expansion causes sunlight to fall outside of the visible spectrum, or in fact, a lot of light. So the premise that was made by Olber's paradox, why isn't the sky dark, is actually, we've proven that it is the way it looks as it does for a very good whole set of reasons. But I thought it was a very interesting thing to end with here. So my summary, dark objects at night are every bit as interesting as the bright stuff. Some of the most interesting work taking place today in physics and astronomy is trying to understand what we can't see, as in dark matter and dark energy. We can appreciate that the fact is that sky at night is dark, and it helps confirm our understanding of the size of the universe. And if the visible light from the Milky Way's core were not obscured, we would see far fewer interesting objects in the night sky, obliterated by that bright core. In fact, I think they said it would be 200 times brighter than the full moon. So, and then happy holidays. So I want to just give credits. So I always give credit to my dogs. Balti is my research assistant. Zero is my research constraint. So you can see me feeding him there. And I try to keep track of the places I get my information, but I'm sure I missed some. But my phone does a pretty good job of keeping me honest. So, and I'm going to end with a quote that I liked from Carl Sagan.
Yeah.
Somewhere something incredible is waiting to be discovered. Ooh, this slide got messed up when I converted it. I apologize. I created Apple software, and when I converted it, messed up. Sorry, I didn't notice in time.
I loved Carl.
Yeah, I think we all love Carl. And that's it, folks. Thank you for listening. If you have any questions, we'll be happy to take them. And oh, by the way, I have Milky Ways. Anybody want them?
Yeah.
So, Melinda, I have a question.
Yes, ma'am.
So one of the boys, is it dust? It's saying dust and whatever is what it's obscuring.
You mean the Boötes void? No, there's literally nothing there. Or very, very little compared to what the expectation is for that large a section of space. There are like 60 galaxies in that void, and there should be over 2,000 given the space. So it's just literally not there, and we really don't know why.
So they found out about that by using non-visible light, X-rays or infrared or something, to find the galaxies behind it.
I think they were doing they originally discovered it doing a redshift study, so they could tell what distance it was. Everything, they placed distances by the redshift, and they could just tell there was nothing there. It's not obscured; it's just empty.
Yeah, but the redshift implies that if they see something.
Well, they see stuff beyond it, and they see stuff in front of it. But they can tell that in that area, that has kind of a spherical area, that area is very, very scant in terms of what's there of normal matter. Yes, ma'am.
Wondering, does dark matter and dark energy only exist out in space, or could it be like
Around us?
Yeah, here on
I
Earth?
don't think we know for sure.
I mean,
Dark energy is supposedly ubiquitous, so it must be in some sense around us. Dark matter, probably not, because it tends to be centered around the middle of the earth.
Dark matter kind of clumps around
Clumps.
large objects.
Yeah,
So Earth is not that large, but it's still large enough
It might have a tiny
Some-
bit, yeah, that's a good point.
I mean, maybe it's just always been here and we just don't notice.
Well, with dark energy, which is the one that's most likely to be around us, we have no idea what we're even looking for yet. It's that early in our understanding. Yeah, we've learned properties of it, we know how much is out there, we know, but we have no idea what it is. This big question.
So if we discover we won't have coffee in the morning, we'll have dark matter.
Hey,
Not if you put cream in.
I'm not a coffee. Yes. Frank.
So that'd be something that, yeah, we even, for, yeah, Barnard object. Number 58. Okay, is that like something moving inward, that like being pulled in? Or is that just gonna be like that?
To be honest, I'm not sure what its motion is, but it's definitely closer to us than the who's behind it. So there may not be any gravitational connection between it and what's behind it. It just happens to be this blob that's obscuring everything behind it. And I don't know, does anybody else know more about Barnard 68 than I do?
It's just,
Yes, ma'am.
I understand this correctly, right? But like I'm kind of thinking, right? So like dark matter would be like theoretically something tangible, whereas dark energy would just kind of be like the air, like not tangible, like not something you can touch.
That's probably as good a description as anybody has.
That's my daughter.
I'll take it, man.
She's good. She's
Yeah.
a good question.
Does anybody disagree or have a better description? I'm game. But all right. Well, thanks everybody.
Thank you.
Have a wonderful holiday season.